Today, we're going to crack open one of the most important ideas in all of modern AI, the network that finally learned how to remember. Let's get right into it. You ever wonder about that? That little bit of magic when you start typing and your phone just knows what you're going to say next? Well, that's not magic, it's memory. But for the longest time, giving an AI a reliable, long-term memory was one of the absolute toughest challenges in the field. To understand how we finally solved it, we first need to meet the original hero of this story. So, our quest for memories starts with this really clever idea called the Recurrent Neural Network, or RNN for short. Scientists came up with it to understand things that happen in a sequence, like the words in a sentence, the notes in a piece of music, or even the movements of the stock market. Okay, so here's the core idea. An RNN works by taking a piece of information, doing something with it, and then, this is the key part, feeding its own output back into itself as it moves to the next piece of info. That little loop is its memory. It's basically remembering what it just saw to help it understand what it's seeing right now. The easiest way to picture this is like a chain, right? When you read a sentence, you don't just see a big jumble of words. You process them one by one. And your understanding of the end of the sentence totally depends on you remembering the beginning. Well, the RNN tries to do the exact same thing. It passes the context from one link to the next. But our hero here had a fatal flaw. Yeah, see, while the RNN was pretty good at remembering stuff that just happened, its memory faded, and it faded surprisingly fast. This turned out to be a massive problem for learning from long sequences, where the most important clues could be really, really far apart. I mean, think about a sentence like this. Born in a small village in Germany, she later became a world-renowned scientist and spoke fluent. So, what language does she speak? You and I know it's probably German because we remember the very first part of the sentence. But an early RNN? It would have completely forgotten about Germany by the time it got to the end. So, how does it ever learn? Well, when a network gets something wrong, it sends a correction signal, we'll call it an error signal, backwards through its own memory to try and fix itself. And when it starts, that signal is strong, it's clear. But here's where that fatal flaw kicks in. With every single step it takes back through the RNN's memory, that signal gets a little bit weaker, a little more watered down. The message starts to get lost. And after just a few steps, that signal can fade into, well, almost nothing. It completely vanishes. And that means the network has no way to learn from things that happened in the distant past. Its long-term memory is basically broken. Now, this crippling problem has a name. It's called the Vanishing Gradient problem, and gradient here is just the technical term for that learning signal. You see, each step backwards involves a bit of math, and when you keep multiplying small numbers by small numbers, the signal just shrinks exponentially fast. The game of telephone is a perfect analogy. The original message gets totally garbled by the time it reaches the end of the line, so it was clear we needed a whole new approach. And that brings us to the real hero of our story today, the Long Short-Term Memory Network, or LSTM. It was developed way back in 1997 by Sepp Hochreiter and Jürgen Schmidhuber, and it was this revolutionary new design built around one absolutely brilliant core idea. They called this idea the constant error carousel, and trust me, it was a total game changer. The big leap forward was to stop trying to force everything through that one leaky chain. Instead, the CEC acts like a dedicated express memory lane, an information superhighway that runs right alongside the main network. Info on this superhighway can travel huge distances back in time without fading away or getting corrupted. So, how does the network control what gets on and off this highway? It uses intelligent gates. The LSTM cell has these special little components that act like gatekeepers. You've got the input gate, which looks at new information and decides, hey, is this important enough to save onto our memory superhighway? And then you have the output gate, which decides which parts of that memory are actually useful for the job we're doing right now. And this comparison just makes it so clear. On the left, you've got the simple RNN with its single, leaky path where everything gets all jumbled up. But on the right, you see the LSTM. It has that protected memory cell, the superhighway, with gates that have total control over what goes in and what comes out. It's just a way more sophisticated system. So what's the payoff for this new design? Well, this whole gated structure protects the memory. It lets the network learn from things that happened thousands of steps in the past. It becomes a master of context. It learns what's important to remember, what's just noise to ignore, and exactly when to pull out a specific memory. But hey, talk is cheap. How did they actually prove that this thing worked? Researchers went to work and designed a series of, frankly, brutal tests. They were specifically engineered to make a standard RNN completely fail. The whole goal was to see if the LSTM could finally handle what we call true long-term dependencies. They created these wild challenges, like the adding problem, where the network had to see two numbers at the very beginning of a long random sequence, and then, way later, it had to output their sum. Or the temporal order problem, where it had to remember the specific order of two symbols that were separated by a ton of distracting noise. I mean, these tasks were just impossible for an RNN. And the results? They were just stunning. This chart really says it all. Where the traditional RNN completely failed, its accuracy basically flatlined. The LSTM solved these long dependency problems with ease. This was it. This was the proof. We had finally built a network that could genuinely remember. So why should a computer science breakthrough from the 90s matter to you right now? Because that success story is the reason so much of the technology we use every single day actually works. Remember your phone's autocomplete? Yep. That's an LSTM under the hood, remembering the patterns of how you speak to predict your next word. When you use a translation app, LSTMs are understanding the context of your whole sentence to give you a much better translation. And when you talk to a voice assistant, LSTMs help it remember the beginning of your command to understand the end. This breakthrough is literally everywhere. And the design just kept getting smarter. In this kind of counterintuitive but brilliant move, researchers added a third gate, the forget gate. And its job is just as important as remembering. It learns when to wipe a piece of memory clean. Like, if you start a totally new sentence, it helps the network forget the context from the last one. And this was a profound realization. An effective memory isn't just about what you hold on to. It's also about knowing what to let go of. Ultimately, the LSTM wasn't just a small improvement. It was a fundamental shift. It gave neural networks the power to connect cause and effect across huge stretches of time, which unlocked all these capabilities that were just out of reach before. So this leaves us with a pretty fascinating final thought. We've gone from networks that couldn't remember past a few seconds to building AI with near-perfect recall. As this technology keeps getting better and better, the question for us becomes, what is the one thing, the one rule or one value that we should make sure this powerful new kind of memory never, ever forgets? Thanks for watching.